In today's video, we will cover a topic that took me quite a while to get my head around because managing storage in Kubernetes isn't a trivial thing. I'll explain to you how to manage persistent volumes in Kubernetes, talk about the different storage classes, and show you how to create them by using NFS servers and my cloud storage. And by the way, speaking about cloud storage, this video is sponsored by Civo, a cloud-native service provider, which makes it extremely easy to spin up your own Kubernetes cluster in just about 90 seconds. Civo offers you flexible and fair pricing for Kubernetes, Linux machines, and storage, which you can easily manage through their web interface, an API, a CLI, and automation tools. They also have excellent support and a very supportive community, so if you want to try and test out Civo, just use their free credits when you sign up. And that gives you enough time to check it out. Of course, you will find a link to that in the description down below. So, if you're familiar with containerization, either with Docker or Kubernetes, you should know that containers are immutable. They don't write any information persistently on the disk, and when the container is shut down because it's recreated during a maintenance process or the host goes down, all the changes you have done inside the container's file system are completely gone. And this isn't necessarily a problem for all applications, so sometimes applications don't need to store data on the disk in order to function. These applications are also called stateless applications, and they don't rely on any persistent storage system in the background. They are often microservices, APIs, or helper containers, so you don't need to mess around with storage here. But most applications will need to store data somewhere. Usually all databases, web servers, or any application that needs to remember changes are stateful applications. And they need to write all these changes persistently onto the disk because when the container is shut down and recreated, it should have the same state as before. Otherwise, you might lose important data of your application and it might not function properly anymore. In Kubernetes, we use volumes to mount a persistent storage location into the container's file system where our application is running. And then the application can write the data to the files in this location to keep all the changes, even when it's shut down. And Kubernetes allows us to manage these volumes very flexibly. There are different options of how the underlying file system and the storage driver manages these volumes, and they all have their own characteristics. We will cover the most important ones in this video, and we will start with the easiest one, which is just mounting a specific folder stored on the host's hard drive inside the port where our application is running. So first of all, I will start with deploying a very simple Nginx web server inside my Kubernetes cluster, and I want to make sure that all the data, for example any websites, are stored on a persistent location onto the node's local hard drive. And by the way, you also find all the different templates for the YAML manifests in my GitHub repository, so if you want to follow the tutorial along, just follow me on GitHub. You will find a link in the description down below, and then navigate to my boilerplates repository and go to the Kubernetes templates PV and PVC folder, and there you find all the different files I'm using in this tutorial, and you can easily follow along. You should be already familiar with deployment manifests like this, but if you are not, in case Kubernetes is completely new to you and you want to have a guided walkthrough, then just check out my Kubernetes tutorial here on the YouTube channel. Of course, I also put you a link in the description. And you can see this simple deployment manifest will deploy an Nginx web server. First of all, I want to give it a name that is called local web, and also set the replicas to 1 because this is a single node Kubernetes deployment, and also the selectors and templates should be new to you. Here in the specifications is the important part. So first of all, we define our containers in the port we are running. So we start with a local web container that is running an Nginx image, and we want to expose the containers port 80. So I'm not using this to expose this to the public internet. I just want to demonstrate how the volumes work. So the important part comes here in the container when we go to the section volume mounts. And this mounts a specific volume inside the container's file system. And you should also place the name of the volume you're using. So in this case, I defined a volume that is called local, and mount the entire volume inside the container's file system path that is located here. So this is not the path on the host system, this is the path inside the containers file system. And you can see in the next specification where we define our volume, we set the name to local, so those two names should always match. And here we define the type of the volume. And you can see the host path represents a directory on the host. So this is usually located in this path, but you could also think about storing the data for the web server on a different location. For example, you can also store this in var nginx server, for example, right? And all the files located here on the nodes file system will be mounted into the containers file system to this specific location. Let me demonstrate how that works by deploying this deployment. So when you're connected to your Kubernetes cluster and when into your project folder where the manifest file is located, you simply can apply this YAML manifest, which is called local-web.yaml, and let's hit enter to deploy these resources. And once this has been created, you can query all pods that are currently running here, and you should see that there is a new pod actually running on our container that is called local web, and this is ready and up and running. So let's try to open a shell inside the container, because then I can demonstrate how the persistent volume will work here. You can launch a shell by using the kubectl command execute and launch an interactive terminal into the pod, and then with a double dash set a specific command you want to execute. In our example, we will just open a bash terminal inside the container. So it's important to understand we are not on the Kubernetes node itself, we are just inside the container here. But when we go to the location where we have mounted the host path, you can see that there currently is no file in here. But if I create a file, for example, let's create a default.html website. This is where you put all the website data for the nginx server. So when we now destroy and recreate the deployment, our files should be still there in this location because it's actually stored on the nodes file system. So let's try to do that. So first of all, we need to exit the shell, and then we delete the deployment local web and simply just create another deployment. So this will completely terminate all running containers and create new ones here. And to open a shell, I also need to get the new identifier of the pod here, copy this, and open a shell inside our new pod as well. And if we query the files inside this location, you can see that our default HTML website is still there, even though we completely deleted the deployment and recreated it. Okay, so you see, mounting a specific location on the host's hard drive into a pod isn't too complicated, and it works pretty well for a single host environment. But using the local hard drive of the host's file system isn't probably the best option to store data in a cluster, because usually Kubernetes clusters have different nodes, and you want to make sure that your data is available for pods across all the nodes in the cluster. So if you just use the local hard drive of a node, pods running on other nodes, they don't have any access to the same storage location. In a high availability setup where you want to scale your applications or achieve fault tolerance, this isn't a reliable option. And here we would need a shared storage independently from the nodes where all the pods have access to the same data. To define such a shared storage, we need to add some additional objects in Kubernetes. So first of all, we need to define a persistent volume, and that tells Kubernetes how much storage is available and how to talk to the backend. The storage class defines the type of the storage backend, which Kubernetes supports in various ways. In the Kubernetes documentation, you'll find examples for these type of storage classes like AWS, Azure, and Google Cloud Storages, GlusterFS, NFS Storage OS, and so on. There also exists a local storage class, so you could also create a persistent volume that stores data on a node's hard drive. But as we've learned, it makes much more sense to use a storage class that talks to a reliable storage backend, such as an NFS server or cloud storage. And once you have defined your persistent volume with all the specifications and the storage class, you need to give your pods access to it, and that's done by creating a persistent volume claim. This allows individual pods to claim a persistent volume and store data on it. So let's take a look how to create such a persistent volume via NFS and attach our web server by using a persistent volume claim. And here we will create our persistent volume resource inside the Kubernetes cluster and give it a name, for example, NFS here. And in the specifications of our persistent volume, we first of all need to specify the capacity, so how much storage is available in that persistent volume and how much can you distribute to your application. You can give that any size from megabytes to gigabytes to even terabytes. In this example, I just use 500 megabytes. And then we also need to define the access mode here. So the access mode specifies how the pod can actually access the persistent volume. And it's very important to understand the different access modes in Kubernetes because they have their own characteristics. You find some details in the official Kubernetes documentation. Let's go quickly through that. So you can see there are read write once, read only many, read write many, and read write one pod. Oh man. And this defines exactly how the pods can access their persistent volume. And it's important to understand that not all storage classes or storage backends support all the different types of access modes. So for example, an NFS server can support almost everything, but other storage classes might not support a read-write many. So for example, some cloud providers only support the read-write once mode, and this is very important to consider because when you set the access mode to read-write once, the volume can be mounted as read-write by a single node, but you can't access the same persistent volumes across different nodes. So an NFS server almost supports everything. So in our manifest, we can define the access mode to read write many, even though we don't need it now, and set the storage class name to NFS. So the storage class name here is not actually important to define. This is an NFS volume. We define it in this section here. And this section here is telling Kubernetes that this persistent volume should be accessed via the NFS protocol. And I just created a new Linux host where I installed Ubuntu and an NFS server and provided some shared storage for my Kubernetes cluster. So this NFS server is running outside of Kubernetes and it's using this specific IP address. So I can define the server IP address here. You could also set up a host name and also set the path where the data is stored on the actual NFS server. So let's take a look how that looks when we deploy this manifest. So once our persistent volume has been created, you can get the persistent volumes by using the command get PV. And then you can see all the different persistent volumes in your Kubernetes cluster. So it's important to understand that persistent volumes are not bound to a specific namespace. So whenever you create those persistent volumes or you're querying them, you always get back the results of the entire Kubernetes cluster. So all the different persistent volumes that are existing here. And you can also see that I'm running several persistent volumes here on my cluster. You can see these have a different storage backend or a different storage type than the NFS volume, which is located here. And you can see that the status of this persistent volume is available. So it's not bound yet to a persistent volume claim. And it also set up the access mode to read or write many and the capacity to 500 megabytes. So now let's start creating our persistent volume claim so we can access this persistent volume to store our data here. And the persistent volume claim is very simple to declare. So you simply create a new persistent volume claim with the name NFS, for example, set up the access mode. And here the storage class name is very important because when you set the storage class name to NFS, and if you want to request some resources, you can also specify some specific parameters like a storage capacity, for example. And what actually happens when we try to deploy this persistent volume claim is the Kubernetes now looks if there is a persistent volume that matches our persistent volume claim requirements like the storage. So it will try to look if there is an NFS volume or if there is a volume with the storage class NFS that has all these different requirements. And then it will bind the persistent volume claim to the persistent volume and they are then bound together. So when we go to the terminal and when we apply our persistent volume claim here, you can see that when this is done and we query our resources now, you can see that our persistent volume is now in the status bound and it's bound to this specific volume claim that we have just created with the name NFS. And you can also query the persistent volume claims here with PVC, and then you should also see the different claims. So it's important to know that the persistent volume claims are bound to a namespace. So it's important to create the persistent volume claims in the same namespace as your deployments or pods are created. And you can also see that the persistent volume claims capacity is set to 500 megabytes because the persistent volume has this storage capacity. It doesn't matter what you specify here. It will not just claim 100 megabytes. It will claim the entire persistent volume. It just looks for any specific requirements and if a persistent volume has a storage capacity of at least 100 megabytes. So now when we want to use this persistent volume now inside our Nginx web server, we need to modify our deployment script slightly. So it's almost the same. I just changed the name to nfs.web, but also the volume mount is actually the same. We mount a new volume with the name NFS into this path on the container's file system. But now we are not specifying an NFS mount here. We are just referring to the persistent volume claim with the name NFS here. And then our deployment will look for this persistent volume claim and it will attach it to the pod. So let's try to apply this as well. And let's also try to get the pods that are currently running. So let's try to open a shell inside this container as well. And let's go to our location where we have mounted our persistent volume. So this persistent volume, you can see, isn't empty. There is a file in here that I've created previously before the tutorial. And you can see that this is actually stored on the NFS server. So for example, if we create another file here, for example, we create just test2, for example, and I now will open a new shell onto my NFS server. You can see when I go to the location where the persistent volume is writing to, you can see our test2 file is also here. And now you can just scale up this deployment up to whatever your requirement is. So you can scale that across different nodes. You can scale that up to how many instances you will need, because we're using a shared storage outside of the Kubernetes cluster that is bound to an NFS volume here. We can just access the same kind of data across all the different pods in the cluster. Okay, so NFS is a great way to provide a shared storage to your Kubernetes cluster, but it also has some drawbacks. The main one is that you need to run an NFS server somewhere. For example, when you're running an NFS server that's running on Kubernetes itself, or maybe on a single node Linux server outside of the cluster, you are fully responsible for managing and securing it. And make sure that your NFS server is high available with minimal downtime, you can support high throughput, and it has a fault tolerance. This is a whole different thing. So in cloud environments, it would make more sense to use cloud storage that's usually well integrated and baked into the Kubernetes provider where you are running the cluster. For example, at Civo, where I'm running my Kubernetes cluster, I can also claim a persistent volume, which will automatically be managed by Civo and attached to my deployments. And then you don't need to manage a separate storage server. You can easily calculate how much a persistent volume on Civo costs you and ensure your data is always well protected and always accessible. So how you're managing cloud storage depends very much on the different storage class types and the different storage backends, whatever the cloud provider is using. On Civo, it is very simple to create a persistent volume with a persistent volume claim and the dynamic provisioning, because on Civo, you don't need to create the persistent volume first, you just create your persistent volume claim, and then it waits for a new deployment or pod to access the data, and it automatically creates a persistent volume for you. So let's take a look how that works. So we will just start with a persistent volume claim and name this Civo. It's important to set the access mode to read-write once here, because Civo's storage backend doesn't support read-write many. So this is something that I've just mentioned before. Not every cloud provider or every storage backend supports all access modes. So if you need a stateful application that's replicated across different nodes in your cluster, you might need to choose a different volume type, or you might use an NFS volume. So it's important to keep all the deployments that are accessing the persistent volume claim on the same node. And we also need to define a storage class here. So our storage class inside Civo will be Civo-volume, and then Kubernetes understands it needs to create the persistent volume with that storage backend here. So now it's important how much we set here, because a persistent volume claim will be created with that same amount of storage we request. And that can be anything from 1 GB up to 100 GB, or how much you actually need. I think 1 GB is the lowest number, so you can't go below that. It will always request at least 1 GB. So let's start deploying this as well. And if we query our resources, you can see that our persistent volume claim has been created, but it's currently in the status pending, and it now waits for our deployment to access this persistent volume claim, and then it automatically will create the storage backend. So for example, if you try to get a persistent volume now, you won't see it because it hasn't been created yet. And you can see that our deployment looks very much the same like our NFS deployment, except one difference, and this is we are using a different persistent volume claim. But the deployment doesn't really care if this is stored on an NFS server or if this is stored on a cloud environment. It doesn't really matter. You just attach your persistent volume claim and mount it into the container's file system. So let's just start deploying this. And if we now query our persistent volume claims, you can see that this sometimes takes some time, so it's still in the pending mode. And if we try to get our pods here, you can see there is a container running, but it's currently in the pending state. So now Civo does the provisioning of the persistent volume in the background because it needs to create this volume onto their cloud storage provider and make this storage available for your cluster, and that can take some time. So when we now get our pods, let's see if that is now up and running, and you can see the container is now creating, but it should have provisioned the persistent volume. So let's try to query our persistent volume claim now. And you can see this is now created and bound to this volume here with a capacity 1 GB, and this is now working. So let's try to get our persistent volumes here, and you should see another volume that is now attached. And you can see there it is. There is a new volume that is bound to our new persistent volume claim with 1 GB, and this is now active and running. Also, the pods should be running now because it actually didn't take so long. And yeah, you can see our pod is also up and running, and all the data for our web server is now stored in our storage backend of the cloud provider. You can also check that when you go to the Civo dashboard, for example, go to your Kubernetes cluster, you should also see all the different persistent volumes that are attached to your cluster, and you can see there should be one of these volumes. I don't know which ID it is, so you would need to query your ID, but you can't do anything with these volumes here. So if you want to release those volumes, you want to delete them, you can see the reclaim policy is always set to delete. So that means whenever you are deleting the persistent volume claim, it will automatically also delete your persistent volume. Okay, so I hope this video helped you to understand persistent volumes in Kubernetes and how to use a reliable storage location for your application data. Now, which storage backend you should use highly depends on your requirements and your setup. And I know there's much more we need to cover in future tutorials because I would love to show you some additional storage options and talk about the different characteristics, but that will be a topic for an upcoming video. This is part of my tutorial series about Kubernetes, so if you want to learn more about it, I've put your suggestion for another great video to watch next in the description, and you should also find the complete playlist on my YouTube channel. So that's it for storage, and thanks everybody for watching. I'll catch you in the next one. Bye bye.